Two pharmaceutical products can follow exactly the same lyophilization cycle and still produce very different results. One produces a strong, elegant cake with efficient drying. The other requires a longer drying cycle or develops quality defects. So where does the difference begin? Not during primary drying, not during secondary drying. It begins much earlier, during freezing. And it all starts with one microscopic event: ice nucleation. As a formulation cools, it does not immediately freeze when it reaches its equilibrium freezing point. Instead, the liquid often continues cooling while remaining completely liquid. This state is known as supercooling. Eventually, a tiny cluster of water molecules becomes stable enough to form the very first ice crystal. This moment is called ice nucleation. Once that first stable nucleus forms, freezing spreads rapidly throughout the product. One microscopic crystal becomes the foundation for the entire frozen structure. Why doesn't water freeze immediately? Because forming an ice crystal requires overcoming an energy barrier. Even below its equilibrium freezing temperature, water molecules remain randomly arranged. Only when enough molecules organize into a stable cluster can crystal growth begin. The greater the degree of supercooling, the greater the thermodynamic driving force for nucleation. Once the critical nucleus forms, freezing proceeds rapidly, and the stored energy is released. This explains why nucleation occurs suddenly rather than gradually. Ice can begin forming in two different ways. In homogeneous nucleation, the first crystal forms spontaneously within the bulk liquid. In heterogeneous nucleation, freezing begins at a surface, such as the vial wall or on microscopic particles suspended in the solution. In pharmaceutical manufacturing, heterogeneous nucleation is by far the dominant mechanism. Glass surfaces and tiny imperfections provide favorable locations where ice crystals can begin forming much more easily. Once nucleation has occurred, crystal growth begins immediately. Water molecules continue attaching to the growing ice lattice, causing the crystals to expand throughout the solution. As ice forms, dissolved solutes cannot enter the crystal structure. Instead, they are pushed into the remaining unfrozen liquid. As freezing progresses, this liquid becomes increasingly concentrated until the entire product is frozen. The final frozen product is not simply ice. It is a highly organized microscopic architecture consisting of ice crystals surrounded by freeze-concentrated regions. The rate of cooling strongly influences the frozen microstructure. Rapid cooling creates many nucleation events. With many crystals competing for available water, each crystal remains relatively small. Slow cooling produces fewer nuclei. Those crystals have more time to grow, resulting in much larger ice crystals. Although both products become completely frozen, their internal structures are fundamentally different. That microscopic difference becomes critically important during drying. During primary drying, ice is removed by sublimation. Every ice crystal leaves behind an empty pore. Large ice crystals produce wide pore channels. Small crystals create much narrower pathways. These pores become the routes through which water vapor escapes from the product. Larger pores reduce resistance to vapor flow and generally shorten primary drying. Smaller pores increase resistance, slowing mass transfer and extending drying time. However, faster drying is not always the objective. The optimal freezing strategy must always balance drying efficiency with product quality and the specific requirements of the formulation. Modern pharmaceutical manufacturing increasingly uses controlled nucleation technologies. Instead of allowing each vial to nucleate randomly, nucleation is initiated under carefully defined process conditions. This reduces vial-to-vial variability. More uniform nucleation produces more consistent ice crystal structures, leading to improved drying behavior, greater batch uniformity, and a more robust manufacturing process. Everything that happens during drying begins with events that occur during freezing. Ice nucleation determines where freezing starts. Crystal growth determines the frozen microstructure. That microstructure becomes the pore network after sublimation. And that pore network ultimately controls vapor transport, drying performance, and product quality. In the next episode, we'll build on this foundation by exploring the water phase diagram, the essential scientific map that explains why pressure and temperature determine whether water exists as ice, liquid, or vapor during pharmaceutical lyophilization.